Hello, cadets. I hope you're doing well. I have to say I'm a little frustrated. This videotaping is challenging. I think it might be my fifth or sixth time, especially when you're at home. You've got a dog barking, maybe somebody walking through. My whiteboard just fell onto the floor. Anyway, we're all doing the best that we can, and I hope you're doing well. Email me if you're having any frustration with anything that is coming out. Hopefully next week, I hope to change my platform into maybe more of a digital whiteboard. I'm having a little trouble with my mouse and making it look nice and neat. So I'm going to resort old school and go with my whiteboard here and continue with that. Even though, you know, I'm a big fan of creative thinking. So we're in the middle of an age where we need somebody to come up with some creative ideas, always. So, you know, from day one, that is something that I have always preached, that we need some creative thinking, right? Problem solving skills. So not only mathematical problem solving, but as we are facing right now, how do we deal with all of these issues that every family, every community is dealing with right now? And, you know, collaboration. So continuing to work together, even in this virtual way. So I hope that you can join me in the office hours sometime soon. If I haven't already seen you, I miss you guys tremendously, and it's always fun to just see your faces. So today I want to focus on the questions that you had in your textbook and go over all of those and clarify some information, and then give you a challenge to challenge you again on your creative thinking skills. So I said we were going to have a physics Olympics. We're going to continue with that. Frankie won on the boat. He had 27 pennies and 2 nickels. So if I didn't announce that, Frankie is our champion. So we're going to continue with our buoyancy forces, answer some more questions with that. Before, let's begin with maybe the St. Michael prayer would be appropriate for where we are right now. So if you can join me in prayer in the name of the Father, and the Son, and the Holy Spirit. St. Michael, the archangel, defend us in battle, be our protection against the wickedness and snares of the devil. May God rebuke him, we humbly pray. And do thou, O Prince of heavenly hosts, by the power of God, thrust into hell Satan and all the evil spirits that prowl about the world, seeking the ruin of souls. Amen. All right, let's get started. So on number 52, so I'm going to make this quick, so I know you guys are busy, but I also want to videotape and not just use a computer, because I definitely, as always, like to show you what we are taking a look at. So you have 3 objects. So in problem number 52, I'm not going to stop. My phone's beeping, so if you hear that vibrating, so many interruptions. 1 jar, right, filled with air, has a certain density to go with it. So, but also a certain volume. When placed in water, so there's my aquarium right there, it will displace a certain amount of fluid. Another jar, same exact size, same exact volume, but a different density. This one is filled with oil, right? Another one, copper, pennies, nickels, dimes, whatever's in there. Again, whatever I could find in the house. 3 jars of all the same volume, but different densities. So what do the different densities mean for each one of these? That means they each have different weights, even though they have the same size, right? But because they have the same size, they can only displace a certain amount of fluid when put into it. The maximum amount of fluid that they can displace will be the same size of this jar. So as long as I don't change the shape of this jar or anything, when I put it into the fluid, it will displace at most this much. But if it is less dense than the material that you're putting it in, right, it may not displace all of the fluid. So here's our jar filled with air. And of course, when I put that into the fluid, it is not going to displace it all. That will float because it's filled with air that is less dense than water, right? Even though the glass isn't, but the volume of the air is what we're really talking about here. You can read in your textbook about how it torques and spins and doesn't stay straight up and down. That has to do with the center of gravity of that. I'm going to place that one there. And of course, this, which has greater density than water, when let go, is going to completely submerge. So I don't want to drop it right now and put that in later, but it, of course, will sink. And when it goes in, it will displace the maximum volume, right? So if the density is greater than that of the fluid that you are putting it in, it will definitely submerge completely. All right, so thinking about that, when we take a look at this question on number 51. All right, so we go back in this way. We take a look at number 51. It has 4 things, right? So you have styrofoam. So remember, the density of water is 1,000 kilograms per meter cubed. So if I take a piece of styrofoam that has a density of 80 kilograms per meter cubed, that density is much less than water. So when I put that in water, similar to our jar of air, right, it is not going to fully submerge itself. It might be like that. So it will only displace this much. But it'll displace enough fluid so that the buoyant force on it is equal to its weight. So let's see, where's my black marker? There we go. So the weight of the styrofoam is going to be very small, but because it's floating, it should have a buoyant force on it that is going to be equal to the weight of this water that got displaced and equal to the weight of the piece of styrofoam. This will float, right? If we take a piece of wood, so in this case, it said the wood has a density. Did I have that right? Or this was 50 and 800, sorry. Still less than water. 50, and this one is 800 kilograms per meter cubed. So this is our wood. This was the styrofoam, right? So the wood's going to do the same thing. It has less density than this. However, close to that of water. So compared to the styrofoam, it's definitely going to displace more in order that it can displace enough water so that the buoyant force is equal to its weight, but this one will have a weight on it that's more than our styrofoam, right? So this will be our weight of the wood, but it'll also have an equal buoyant force acting up on it. So this buoyant force is smaller, bigger, right? But again, they both will float. Now, if we take a look at the lead and the aluminum, both having densities that are greater than that of water, right? So if this is our lead with a density equal to, let's see, I'm sorry, nope, let's go with the aluminum first, 2,700. Aluminum, 2,700. Okay. This one is going to be like our jar of copper pennies, has a greater density than water, right? So it is going to completely submerge itself inside the water. It'll displace it all, but the weight of it, because this is 2,700, is going to be far more than what the buoyant force can be. And at most, the buoyant force is going to be equal to the weight of the fluid here displaced. So this buoyant force on here, because it's going to completely submerge, should be a little bit more. So this should be our third buoyant force, right? But then we take a look at our, I'm going to draw it off to the side here, the lead, which has a density equal to 11,300. All right, 11,300. Then you're going to have a buoyant force. That's going to completely submerge, right? Its weight is going to be huge compared to that, much, much greater density. But its buoyant force cannot be any more than that because it cannot displace any more water than these two. So the most water it can displace is the complete volume. So whether I fill this with pennies or more water or something that's more dense than water, no matter what, even though they both have more weight than the water that displaced, this will have more weight. That does not mean it gets a greater buoyant force on it. The buoyant force is dependent on this volume that I displace. So you answer to number 52. Styrofoam's the least, wood is second. These two are tied. Aluminum and the lead will both have the same amount of buoyant force on them. All right. So number 53, though, if I take all three of these, right, and let's pretend they're all the same. So now let's pretend they're all empty glasses. And I put them in different materials. Now I will displace a different weight of the fluid. Okay. So in this case, remember that the buoyant force is equal to the density of the fluid times the volume displaced times G. So in problem number 53, we take 4 objects, right? All of the same size, but we're going to put them into different things. So oak has a density of 900 kilograms, and we're going to put that in olive oil. So if this density is 900 kilograms, and we put it into olive oil, right? Olive oil has a density of 880, so this is our wood. So the fluid only has a density of 880. They're both going to displace the same amount of volume. This will definitely sink, right? So the free body diagram on this would be that the weight is always going to be more than the buoyant force because its density, which is that of oak, is greater than the olive oil. So that would be on the first one. Alcohol, if we take a look at alcohol, has a density of 790, even less, right? So alcohol, 790, right? So I'm going to displace the same volume, right? But in that case, the weight of the wood hasn't changed, but the buoyant force is going to be less because I'm going to displace the same amount of volume, but my buoyant force depends on the density of the fluid. So it's going to have less density or less buoyant force on it. However, when I submerge it in mercury, that's going to be the most, right? So let's see, water, I forgot that water was on there. So water with 1,000, so we have that up here with 1,000, right? So same thing. So this would be if it's an alcohol. And this was in the oil. And this is in the water. So let's actually, I'm going to start all over again here, make your chart like this. All right, don't have enough room. I need my whole board in the room. So buoyant force is equal to the density of the fluid times volume times G, right? So water has a density of 1,000. And what else did we have here? Oil, a density of 880. And then we have alcohol with a density of 790, and mercury with a density of 13,600, all kilograms per meter cubed. All right. So because our piece of wood is all the same size, right? What's going to happen? When we put it in the alcohol, it's going to have so much weight, right? But the buoyant force on it is never going to be enough to overcome the weight. This would have the least. So that would be our fourth one if we were to rank them. Our oil, okay, so this is our alcohol. When we take a look at the oil, what should not change is that your weight stays the same. This is more dense, so its buoyant force, 880 times the volume, is going to be more. So that's going to be a little bit more, but weight should be more than that. So it should not be able to float in there. So you still have weight greater than your buoyant force. Because even if I take out that same volume, because this density is less, it cannot have a buoyant force that is equal to or more than its weight. However then, so this would be 3. When I submerge it in water, since it is less dense, it will not. What's going to happen there? When I put it in the water, the weight is going to stay the same. And water is more dense, so the water, it will not be completely submerged, and our buoyant force will be equal to the weight in that case. Whereas when I put it into the mercury, so this would be our second highest buoyant force, and then when not highest buoyant force, but when I put it into the mercury, The difference is in mercury, it's not going to have to displace much mercury, but it'll still float. So the buoyant force on that shall be also equal. So in both of these cases, for the mercury in the water, the buoyant force on them will be equal. So it says rank the buoyant forces in the liquids exert on the cubes from the largest to the smallest. So in this case, they will be equal, right? So we should say these two are equal. This one will have the smallest buoyant force, second smallest force, so fourth as far as the smallest. Next, these two are tied. I hope that makes sense, right? All right, number 59. Okay, so in this case, we are drawing what the buoyant force is going to look like on each one of these. So you have the same fluid. Oh! See the pains I'm going through to do all this for you all? You better appreciate it. Oh, this is crazy. That's what happened the last time, but I'm not going to erase it. So let's get going. All right, so on this one, here we go. I want to rush through this because I really didn't want this to be any more than 15 minutes. All right, so let's take a look at 59. So very easily, in this case, what's happening here? Here's our fluid, right? So you have this one that is submerged, right? This one that is just underneath it. This one is not submerged. This one is ranked all the way to the bottom, and then you have this one halfway. So A, B, C, and D. What's going on in each one of these? All right, so in each one of these, right, buoyant force, the weight. So you're told, I believe in this one, each of it at rest. Object A is partially submerged. Object B and C are totally submerged in the same of the liquid. Draw a force diagram for each object. Rank the densities of the object from least to greatest and indicate whether the objects have the same density. So in this case, the weight of A and the buoyant force are equal. It did not have to displace very much fluid. So therefore, this would be your least dense. Because it's out of the water, right? So it's less dense than water. This one completely sinks, which means its weight must be more than the buoyant force. This buoyant force is more than that one because it completely is submerged. So in this case, C is the most dense. Okay. And over here, the weight of B and the weight of D should be more than that of A, but not as much as C, but B and D are both completely submerged and floating. So it doesn't matter where in the fluid you are floating. You can float at the top or in the middle or right before you hit the bottom, but the buoyant force on it is the same. Once I'm completely submerged, I don't increase my buoyant force as I go deeper because I cannot displace any more fluid. So these buoyant forces are equal. They are floating. So B and C are the same. C doesn't experience any more buoyant force than B and D if they are of the same size. However, C has a greater density because it has sunk to the bottom and has greater weight. All right? All right, let's see if I can erase this without knocking down this board again. Oh my goodness gracious. Maybe that'll be my question. Who saw the board collapse at the end, right? That'll be my test on who watched the whole video. which I don't really care if you watch the whole thing or not. I just want to provide you the opportunity to explain these problems. All right, let's see if we can get through 59 pretty quickly here, seeing how much time that we have. Let's see. Looks good. All right, so on 55, rather, a 30-kilogram ball with a volume of 37.5 centimeters cubes is attached to the bottom of a glass beaker with a light string. When the beaker is filled with water, the ball floats fully submerged under the water surface. Draw a force diagram for the ball and determine the force exerted on the ball by the string. All right, so step number one, what do? Draw a picture, right? So we're going to draw a picture. So here we go. We have a beaker filled with water, right? And we have a ball inside the beaker, right? Tied to the bottom. So force diagram on the ball. What's going to be taking place on this ball? So if we were to just look at the ball, what would be the forces that are acting on that ball? So first of all, would there be weight? And the answer is yes. There would definitely be weight acting on that ball. Would there be a normal force? No, it's not sitting on anything. Would there be friction? No friction. Would there be tension? And the answer is yes. And remember, the tension can only pull. Tension cannot push. So there is a tension force pulling down on this. No air resistance, no applied force from anything else. And then remember, number 7, what is the special force that might be mentioned, which in this case would be your buoyant force. So what is the buoyant force that is acting, and how is it acting? And it's going to push it up like that. It is in equilibrium, so it's not moving anywhere. So what we do know is acceleration is equal to 0, right? In the y, if we do Newton's laws and say summation of forces in the y equals ma, that is equal to 0. You'd have your buoyant force minus tension minus weight equals 0, right? So remember, draw a picture, list what you know. What does that look like? So there's our forces that are acting on that ball. So next we list what we know, right? What were we given? The mass of the ball, right? So our mass of the ball, we can start over here, would be 30 grams, which is 0.03 kilograms. So from that right away, I can solve for its weight, which is going to be mg. So the weight of the ball is going to be 0.03 kilograms times 9.8 meters per second squared. So the weight of that ball is equal to 0.29 newtons, right? So nothing different than we haven't done already. So that's the weight of our ball there. All right, so that gives us this, right? So if the question is, what is the tension, right? That's what we're looking for. What is the final tension? So if we use this equation to solve for that, the buoyant force minus the weight equals tension. So we know weight, now we have to find the buoyant force. So I'm going to write our weight down, minus 294 newtons, just to give me space. So now we're going to get rid of that. Right? And we want to find what is the buoyant force. So remember, the buoyant force is equal to the weight of the water displaced. So the buoyant force is equal to the density of water times the volume of water displaced times g. So what you were told here, right, it's a 37.5 cubic centimeter ball. So the volume of this ball is equal to 37.5 cubic centimeters. So right away we want to say, well, we don't want cubic centimeters, we want cubic meters, right? So we need to multiply this. Be careful. There are 100 centimeters in 1 meter. So we must cube that. So whenever this is squared or cubed, you must do that to your dimension when you're multiplying by that. So instead, you're dividing by 100 cubed, not just 100. So the volume in meters cubed of that ball would be 3.75 times 10 to the minus 5 meters cubed. 10 to the minus 5th meters cubed. So that's the volume we're going to use here because it is completely submerged. So the volume of this ball is also equal to the volume of the water displaced. The density of water is 1,000 kilograms per meter cubed. And we always know G to be 9.8 meters per second squared. So plugging all that into this equation gives us our buoyant force. So we get 1,000 kilograms per meter cubed times our volume, which is 3.75 times 10 to the minus 5th meters cubed times 9.8 meters per second squared. Multiplying that all together, running out of space here, our buoyant force is equal to 0.3675 newtons. Okay, 0.3675 newtons. When you erase that again, use that over here, plug it in, and then we can solve for our tension in our rope. So that's our buoyant force. Pulling back down on it is this, which gives us our tension of why it has to pull, because that ball wants to pop back up, right? So our total tension, once we plug that all in, it's 0.0735 newtons is equal to T. There you go. I'm sorry, I'm not a producer, I'm not a movie star or anything like that. Craziness, and I'm not doing it again. Hopefully you understand. All right, so work through that problem over and over again. Work through all the problems. I have posted solutions to these written out, so you can also print that out because I know I erased things here. So I have that on paper and that is posted under our class documents. So my challenge for you today, let me demonstrate a little bit about what we saw here. Okay, oh, I thought it stopped the recording. All right, let's go back to this. So in our problem, so here I have a jar that has a it has a balloon to it, right? So this one I filled with some water so that it's not air. There is water in there so that I know it'll sink because of the water. So there's an example of what you just saw in our problem. It only displays so much, right? So my question to you is, if I give you the dimensions, which I will put on our announcements, if the dimensions of this balloon give you the radius or the diameter of it, therefore you can figure out the volume of this balloon so that if I completely submerge it, how much mass do I need to put inside my jar in order that it's going to pull down on this, causing it to be completely submerged. So look what's happening to the water height as I push that down. See our water height going up and down? All right, so that's my challenge for you. Who can give me the right answer? You see the string connected to that, right? How much mass do I have to put inside my jar so that it'll completely pull this balloon down and still float? So I want it to still be floating, not just completely sinking, because obviously you can put in 1,000 kilograms and it'll pull that down. But I'm going to fill this completely full so that the balloon is completely submerged and our jar, as you can see right there, is floating, not touching the bottom. Hopefully that works. So I don't know, tomorrow's Wednesday, or today when you're watching this should be Wednesday. And let's say by Friday you get me an answer to that and we'll test it all out. All right. Thank you for your patience, and we'll talk to you soon. Take care.